We will continue with query processing this time. So last time we looked at very important general classes of algorithms. One is the simple hash join. That's the most frequent join being used in main memory systems. So very simple idea. You build a hash table on the left input, or it could be the right input. You can make a decision based on, for instance, how big is the input that you want to build the hash table on, and then you might take the smaller one, for instance. And then once you did that, like in this line, you probe each and every tuple from the other relation against that hash table. So you query the hash table with that S element in that example, and if there's a result, you output that to the result set. That's a very easy way of doing a join, called simple hash join. And there are thousands of parameters. You can vary, for instance, the type of hash table to use would be one. Is it thread safe, yes or no? We talked about a parallelization example for that last time. Okay, then we looked at the sort merge join. So this idea that when you do a join, you sort both inputs on the join key that's shown in this example. And of course, there could be the situation that the stuff is already sorted, or one of the relations is already sorted on the join key. Then this join gets much cheaper. But in the general case, you have to sort on both. Then you keep those pointers, one for each input. And then you always move the smaller pointer forward. You have to be careful with foreign key relationship things. So here, the important trick is also when deciding which pointer to move forward, you always move that pointer forward that points to the foreign key column, this one. Yeah? Here you have duplicates. If you would point the other, if you're in a situation like 0, 0, and you move this PS pointer first, then you would be here and wouldn't find the other results of the zeros on the left with the 0 on the right anymore. No? So that's important. And that join, and then we had here a very long animation on that. I will skip over that. Oh, so many slides. Right, and then we started looking at co-grouping. That's a very nice, algorithmically, it's a beautiful concept. It appears all over the place, solves many problems. And the idea here is, if the input is sorted, well, basically you could say, well, all the tuples that have a 1 belong to one group. So if you group this customer's relation on city ID, group by city ID, yeah, all these tuples would go to group 1, those would go to group 9, and so forth and so forth. So the difference to a standard group by, where you always only group on one relation, is here you group on multiple relations, 2 in this case. Yeah, yeah, the group this one on city ID, this one on this foreign key, and then you can only find join results within this co-group, as we call it. Yeah? Only by joining those tuples with those tuples, you may find results. It's impossible that you find results from here to there or results from here to there. Yeah? So that's a very algorithmically very good idea. And yeah, you can do it with sorting, without sorting, of course. And in the end, it leads to an algorithm like that. So that's a high-level pseudocode for that. And I told you already last time, this reappears all over the place with different names. It's always the same idea. There's a partitioning phase. Without looking at the details here, we start first with an example. So you first partition, and then you join each core group individually. I had it on the blackboard in the lab on Friday, but I prepared some more slides to show you how it works. So assume we want to run one special case of the core group algorithm on this join. So we have R on the left and S on the right. And maybe I have like 8 memory pages, as depicted here. So the first thing I need to do is to partition the input R. And R can be much bigger than my available main memory. Yeah? Actually, the minimum size you require for that is 3 pages. With 3 pages of memory, you can partition any data set. Yeah? Because you can always, maybe I first explain how I divide the memory. So how you do that is you keep 1 page for the input data and 1 page for the output data. So as I have 8 pages here, I have 1 input page spent here. So I have 7 pages left. Yeah? So this is 1, 2, 3, 4, 5, 6, 7 pages for the outputs. And then basically what the algorithm does for partitioning, it's also called external partitioning, is you always read 1 page from R, doesn't have to be the first one, typically from beginning to end, put it here, inspect the tuples, and distribute the tuples depending on your partitioning function, city ID in this case. Yeah? So one tuple might go here, another there, and so forth. Whenever such an output page is full, you send it to disk. Yeah? You write it to an output stream, also called an external run, or just run for short. Yeah? These guys here. And you start all over with a with an empty page. Yeah? So when this gets empty, of course, yeah, you load the next page from R into this page in main memory, distribute the data to the output pages, and so forth, and so forth. Yeah? And of course, this only makes sense if you have at least 3 pages of main memory available. Yeah? Because with 3, you can have a fan out of 2, meaning 1 input page, and there will be 2 output pages. And of course, you can recurse. Yeah? You can recurse this processor. If you feel like, okay, this is still too big for what I have in mind, you partition it even further. Yeah? You go into recursive partitioning. That's not what I'm showing here on this slide. Here I only have one partitioning step. And the trick for co-group join is basically that you use the same partitioning function on both sides. So once I'm done partitioning, I'm in this situation. Now I have the entire input R partitioned into horizontal partitions. Yeah? The union over all of those subsets would give me R again. I can throw R away if you want. Yeah? I don't need that anymore. Who cares? Yeah? But now I do the same thing with S. Yeah? So I partition it, basically mirrored, the same algorithm, visually mirrored. So again here, using the same partitioning function. In this example, it's only 8 pages. Of course, you would have more available. Well, you do that, partition it with all your memory, and then you end up with that. Now you have partitions from R, partitions from S, and you have co-groups. Those are the co-groups you build. They belong together. Only within a co-group you can find join results. So the next phase in the algorithm is to compute joins on those co-groups. So you start maybe with co-group 0 and join R0 with S0 using whatever method you deem suitable. Yeah? In the lab on Friday I showed, you could use simple hash join. Yeah? So as long as you partition such that any of those relations fits in main memory. So if for each co-group you have the condition that either R0 fits into main memory or S0 fits into main memory, you can run simple hash join. Yeah? Because simple hash join, you create a hash table on one of the inputs and the other is probed against. So that's important to understand for simple hash join. Simple hash join doesn't require you to load all the data in main memory. As long as you can build a hash table on one of the inputs, it's fine. The other can be petabytes big. Yeah? You just probe it against it. But you don't have to keep all the data from the probing relation in memory at all times. Yeah, that's basically the algorithm. And then once you're done, you continue with co-group 1, co-group 2, and so forth, and so forth. Yeah, that's one example for co-group join. Yeah, is that clear? Maybe let's briefly look at the pseudocode. Yeah, basically here, some terminology. There's a build input and a probe input. That's old terminology. But basically what I do is I partition those both inputs here using the same partitioning function. That's this first phase I showed on the left. It's this thing. On the right is that thing. And then basically for each co-group or group as it is called in this pseudocode, I run an algorithm. For instance, I retrieve here the left input, I retrieve the right input, and feeds that into some algorithm. We will look later on, of course, if you compare that to what I just told you, if this means here that you materialize the left input in my memory fully, and then you materialize the right input in memory fully, then you can't do what I just explained to you. I said, okay, if one of the relations doesn't fit in main memory, you have one relation is 1 megabyte, you build the hash table on, and the other relation is 1 terabyte, and you do here something like that you load that data into main memory, that's not going to work. So you need some sort of pipelining concept here to make that happen. We will look at that later on in today's lecture, I think. Okay, that's just conceptually how that works. So basically there's a divide and conquer phase where the There's a divide phase. That's a divide and conquer algorithm, a divide phase where the different divisions, the different partitionings on the two inputs are synchronized, if you want to phrase it like that. And then in the second phase, there's this conquer phase, meaning you treat one core group at a time and produce the join results. Yeah, that much about core group join. And then we briefly look at grouping and aggregation. So the good thing about grouping and aggregation is that it's again the same algorithmic patterns. Yeah? You can do a hash-based grouping, and I sketch it here with pseudocode like that. Maybe how do we go through that? So basically what you do is in your hash map that's built on a specific key. You can also do that with any index, but here typically people use a hash map. So as a key, you use a grouping condition, obviously. If you group on foo, the foo attribute of any input relation, foo will be your key in your hash map. And the first thing that you do is you loop over all your inputs from R. So again, recall that grouping, the standard grouping, not the co-grouping, standard grouping is always on a single relation as an input, not two as shown in the co-grouping example. So basically for each tuple, small r from the input capital R, I check whether the attribute I'm grouping on, that is this, in this case it's the attribute X, is already contained as a key. Yeah? If it's not contained, I add a new list to that. I create a new list that I'm calling the group. Yeah? If it's already contained, I get the appropriate entry. So basically what that means is my hash table here is organized as a mapping from key to a list of values. Yeah, and the values are the tuples I want to aggregate. Yeah, that's what you see here. So basically, I'm mapping from key to this list. Yeah. So basically, so if it's contained, I just get that list and I append the new element. If there's no such entry, I have to create a new list. In either case, I then put it to the hash table. So I basically overwrite whatever existed before. And now this key here, the grouping key, points to this list of values. Yeah? So that's the first thing, that's the first phase in the algorithm. You collect, you use the key in the hash table to group these values. And here you also see what often it's misunderstood or confused in the big data engineering lecture. I have many slides on that in the big data engineering lecture because people say, grouping, aggregation, group by, count star average, blah, whatever. Yeah, recall, this is grouping in the SQL and relational algebra is 3 operators at the same time. It's partitioning horizontally. That's what we do here in grouping. This is horizontal partitioning, right? Yeah. Again, like in the co-grouping example, you partition the input relation into chunks based on a specific key. Then comes the second thing. For each group, you want to do something to that group. You want to compute the number of tuples, the count star, in that group. You want to compute the sum over a specific value for each and every group. That's the second part, and that happens here. So for each key existing in the hash map, you get that group. In Python, you get an whatever key value iterator to do that. You could do it simpler. And then you have your aggregation function. That's what I just said. Yeah? You run each and every group through that aggregation function and compute that aggregation result. And there comes the third part of this group by, that is a projection. Yeah? So which are the attributes you're projecting on? What is the format of the tuple you're creating, be it in SQL or relational algebra? And that is why there's 3 operators. Historically done like that, not good, but have to live with that. Yeah, so similar ideas in joins. Yeah, and sort-based grouping again is very similar to this sort-merge join we looked at. Here, of course, I think we don't have to go through each and every detail, but basically, maybe I show it. Let me show that with a more visual example. I think that's a good one. Oh, that's a good one. So let's assume that. I can erase that. Should I? Oh, no, come on. Okay, so don't look at this one. But basically, what you do in sort-based grouping, you keep a pointer, start with the first tuple, so assuming the stuff was sorted on the grouping key, on the group by condition, that's city ID in this example. Yeah, you always compare values as long as the pointer is pointing to the same value. Yeah, you start initializing the pointer with a value you find at the first tuple, that's 0. Yeah, jump to the next, 0 again, jump to the next, 0 again, jump to the next. Oh, there's a 1. Yeah, and then what you do is, aha, a new group is starting. Okay, because the group now has a different key than before. Then you know that everything from the last start position to the last tuple forms a group. Yeah, because they must be adjacent in sort order. You run those algorithms, those tuple, through the aggregation function. That's it, yeah, and start all over. So you start a new group, there's 1, okay, there's 5, okay, this one has to be fed into the aggregation function, stuff like that. Yeah. That's all you do in sort-based grouping. So I hope you get the message. Once you understand how grouping is used in query processing or hashing is used or sort, it's always the same stuff, really, always the same ideas. Yeah. Okay, so I think we can skip over sort-based grouping aggregation. That's what I just showed, right? Yeah, okay, now we can skip over that and look at some other very fundamental algorithm, which is from a time when hardware was really weird in the sense, from our perspective, it had this really small hard disks that were slow, small memories, and but still the algorithm I'm going to show you still applies in every situation where you want to sort data that's bigger than the available main memory. Yeah, you should have seen main memory sorting algorithms, quick sort, merge sort, insertion sort, heap sort, you name it. There are many, many different algorithms that have this precondition. The data to be sorted has to fit into main memory. What if that is not possible? What if the data set is larger than the available main memory? And there we have external merge sort, which applies in that space and is algorithmically interesting and can actually merge into certain database or merged with certain database operations. So this is an example of something that's super fundamental, and that is the reason why I'm showing you that. Yeah? Maybe you will never have the problem that you have to sort data that's bigger than the available main memory given today's main memories. Yeah? It has to be really, really big data. But it teaches you a lot about algorithmic patterns that appear in certain data processing solutions, and that's what I'm showing it. So, okay, I know here I have to swipe left. And so I use a very minimal example here, and the example is that I have 8 pages here. Those are my input pages. On each page I only have 2 integer numbers. Yeah, it's a very, very weird situation. Pages are much bigger than integers, of course, yeah, but just for the sake of simplicity. And yeah, I have empty pages like depicted here, and a page with 2 integers is here, so there's some data. So this is my input file that I want to sort. And how would I do that with external merge sort? So the algorithm basically runs in 2 phases. All of the algorithms I'm showing run in 2 phases, right? No, there are algorithms that run in 1 phase or 3, yeah, but maybe today's algorithms all run in 2 phases. So basically, what you do is you fill up in the first phase, you have the unsorted data, and you create sorted runs from that data, which means you fill up all your available main memory. In this example, it's only 2 pages. Here you have to have at least 2 pages, otherwise it doesn't make sense. That's the absolute minimum for this algorithm. I don't want to do this here. Oh no, I can, yeah. So this is basically visualizing that. That's my main memory I'm using. So you load the data, then you sort the entries in main memory across pages. So you have something like that. Now you have a sorted sequence 2, 3, 4, 6. And then you write the 2 pages out on disk, for instance. And let's assume that the input file sits on an SSD, and the intermediate data I create also will be written to an SSD, yeah? But could be any storage device, doesn't matter. So this output file is called a run. now I have these 2 pages, I just stack them on top of each other with entries 2, 3, and 4, 6. Now I continue, I loop over all of the input pages. So basically, now I fill up my main memory with the next 2 pages here, sort them in my memory. It's just a simplified visualization here. Of course, you can't directly stream it to the output. You first load it into main memory, sort it, write it. You get the idea. Yeah? So you do that for each and every input page, which means eventually you end up with those 2-page runs. 4. Yeah, of course, we had 8 input pages divided by 2. We must have 4 of those. Now you're done with the first phase, or phase 0, or pass 0, as it is called sometimes. Now, what you do is you merge those smaller runs recursively into bigger runs. That happens here. So now, what I do is something. Now, imagine you would see the slide upside down. Can I do this? What is that? Why am I rotating that by 180 degrees? What? Has someone an idea why am I doing that? Maybe mentally also you would invert the arrows. Let's assume the arrows point in the other direction. Haven't we seen something like that before? Someone an idea? Raise your hand and... Yeah? Trees? Yeah, sure. Yeah. That's also, it's called a merge tree. Yeah, you're right. You could map it to a tree, but I mean something different. I just explained today, right? Yeah? Split in the database? Yeah, no, I mean, what did I show? Which algorithms did I show today? 10 minutes ago, or 15. Maybe I make the link here. Now I can switch back and forth between those slides. Cool. So, what was this one? I have to rotate it by, okay, the rotation is wrong. Okay. Sorry. Wrong rotation. Almost, right? Not bad. So here we partitioned. Yeah, so there was an input stream partitioned into 8 output streams, okay? That looks the same, just that the arrows point in the wrong direction. I'm merging, in this case 2, could be 8 input streams into a final output stream. Yeah? So rather than splitting one input stream up into multiple 8 output streams, that's a partitioning operation. I take 8 input streams and 2 in the example and merge them into one output stream. Yeah, it looks like a very different algorithm. Algorithmically, it's the same. It's just the inverse or the mirrored algorithm. And all techniques you can ever use here to make this better, you can equally use to make this one better. That's again an opportunity for laziness to understand, oh, that's the same thing, it's mirrored. Yeah, algorithmically, it's just a counterpart, merging and partitioning. It's also called the dual. Yeah, that's a pair, a dual, partitioning and merging. Yeah, those are like dual operations, as we call them. And if you understand one, you must understand the other. You can't understand just one without understanding the other if you see that those are dual operations. Yeah, so that's very important here. So if we go back to where I just was, here, I was here, right? Change this back to Rotations-Modus. Where's my, here, full screen, okay. Yeah, so now we merge these 2 input streams into one output stream, and you do the same thing. Yeah, just that you have 2 input pages for each input, one input page for each input run, yeah, and one page for the output run. That's the same thing. And when partitioning, I was calling it the fan out. Yeah? The number of streams I'm partitioning to, now I'm calling it the fan in. The number of streams that are partitioned into one output stream. Yeah? So we will also use dual terminology. So I can do that here with 3 pages. Yeah? So if I claimed 2 pages is a minimum here in the first pass 0 phase, I will find out, no, 3 pages for merging is really the absolute bare minimum. You need to do that. Yeah? So I could have used those 3 pages, of course, here in that phase already. Yeah? So I do that, I read those inputs, I create a sorted output stream, which is then, of course, size 4. Yeah, I do the same thing here, sorted output run of page 4. Yeah? Well, then I'm done. Now I have only 2 runs left, yeah? 2 partitions if you want it. Not want it, if you want to call them, there are partitions, horizontal partitions of the data. And then, well, there's only one thing left to do. That's the final merge operation created this final output run on disk. And that's basically the sorted version of the input file. Yeah, that's the external merge sort. Yeah, you get an idea? Oh, I'm so impressed. Yeah. The merging, like in the green box? No, this is just, again, you always have to load 1 page into main memory. This is a bit misleading here, because of course you will lead the first page of each of the input runs to make that happen. Yeah, but you need 1 page for each input run and 1 for the output run. And the merge only makes sense if you have at least 2 input runs. So 2 plus 1 is 3 pages. It's the absolute minimum for merging. Yeah? For the phase 0, for run generation, if you used 1 page of main memory, it doesn't make sense because you would only sort inside those pages. So 2 is the absolute minimum. But if you see the entire thing, of course, well, if you have 3 pages and I use 3 pages for merging anyway, you could have used 3 pages in the beginning, right? Yeah? Other questions? Okay. Yeah, so that's how you sort, yeah, that's algorithmically, I don't know. Okay, let's go back to join algorithms again. So we learned about sort, merge, join, and I said, okay, both inputs have to be sorted. Let's assume both inputs are too big to be sorted in main memory. So that means you have to run sort, merge, join twice for both of the inputs, right? Yeah, sort on R first externally, sort on S first externally, and then feed those sorted runs into the join algorithm to produce the join result. Do you see any opportunity for optimizing that algorithm? If you recall sort merge join, I showed these 2 pointers. Yeah, you always move the pointer pointing to the smallest element. Yeah, and then basically you walk through those sorted streams synchronously, produce join results, and so forth. And now this external merge sort produces sorted output files. Yeah? Yeah, what do you mean before? So I'm saying the problem statement is really you have 2 relations, so it's a 2-way join. You could, in theory, do 4-way joins. Do you mean 4-way merges here? Or? Yeah, how exactly would you do that?
So that it can emit one phase for one pass for writing into the disk.
Yeah, maybe. Yeah, maybe. I mean, one optimization you could think about, okay, Professor Dittrich said you could do co-grouping basically, and if you create co-groups by sorting, why do you split it up into two input sets in the first place? You could basically taint the tuple, mark them, set a bit 0 if it's from R, bit 1 if it's from S, and pipe them through the same external sorting pipeline. Why not? Yeah. Yeah, then you run one of these algorithms and basically put them together already while merging. That's one approach, but I mean something different here. Think about preconditions for a sort-merge join. If I phrase it carefully, I would say, okay, the two sort-merge join as a precondition, or sort-merge join, we typically say that the inputs don't have to be sorted, but if I say merge join, the precondition is both inputs have to be sorted, or to phrase it more precisely, the inputs have to be presented as two sorted input streams. Two sorted input streams. I don't require that the data is available all at once. Yeah, I only step through those streams from one tuple to another. Yeah, but I don't have to materialize the entire streams in main memory. Yeah? As long as I get a stream and I can call on that stream, give me the next element, the next element, the next element, the join algorithm, the merge join algorithm will work. But now you learned about external merge sort, where I create a lot of intermediate data. I mean, let's look at the I/O costs of this. Yeah? Just in terms of not random I/O, but the amount of data being written. So what do I do? In the first phase, of course, I read all of this once, partition it, and write it once. Now for each merge phase, I do the same thing. All of these runs are read once and written once, okay? Yeah, so for each merge, I will have here, for this merge, I have another read and another write. And then I have another read and another write. So I have, if I counted correctly, 3 read operations, 3 times reading the entire data and 3 times writing the entire data. That's a lot of I/O. Maybe costly, depending on your storage system. Anyway, we want to be better, better than that. So do you see any opportunity in the context of the sort-merge join to optimize that? Wild guesses, wild ideas. Just an empty slide, maybe the scribble it here. Okay, so let's assume from R we have 2 sorted runs, okay? That's R. Let's call that as the R input. And those are this is my input from S, also 2 sorted runs. So what I just explained to you, well, I want to have a sorted file containing all of the data. So in the standard external merge sort, you would initialize another merge operation here, feed the streams through that merge operation and create a big sorted output stream. You do that for both, of course. That's what I just explained. Yeah? But if the only thing you require to be able to run a merge join is to have a sorted stream, you could also do it like this. You could say, well, I merge them concurrently at the same time. But rather than sending those outputs to to output files, I directly feed them into the merge join, yeah, producing those results. There's no need to materialize a fully sorted file on disk. Why? Yeah, I only need the sorted stream, so I just stream it directly to this merge operator, and that's a huge difference here, because you completely save one of those writes that you would do in the normal operation. You still have to read all of that stuff, of course, and read interchanging from the YAR input and the S input, but you save one of those write operations, and that may be a huge difference. Yeah? As the interesting thing about sort merge join is that you can play many tricks, and actually on the assignment sheet we will ask you about another trick, whether you have an idea to modify the algorithm slightly to do better things. Yeah? So that's the core algorithm. Maybe if you look at the pseudocode, maybe it makes sense we go through that again. It's so important. So basically, two phases. So this phase 0 and this phase, or pass 0 and passes 1 and following. This pass 0 is also called the run generation phase. If you have your input, you just fill up, take the next pages, fill up all your main memory, run it through a main memory sorting algorithm, quick sort for instance, and write that run out to disk. And what you do is in main memory, you keep a heap with metadata for those runs, not the actual data, but just pointers to those runs in disk, because you later on want to be able to retrieve those files, of course. So basically this generates the run, writes an output file, and then the metadata is added to a heap. So you do that for the entire input until it is exhausted. And then you loop over the heap. Typically, you could organize like that the heap is organized using a half order where the smallest run has the highest priority. Yeah? So from the heap, you always take the smallest runs that exist and feed them to the merge operation. That basically happens here with this operation. So I'm saying I remove k entries from the heap. Those are my inputs. And I use those as inputs into such a merge operation. That will create an output run, and the metadata for that is again added to the heap. And I keep on looping and looping and looping as long as the size of that heap with the metadata is greater, strictly greater 1, because that implies there's more than one run. So I haven't fully merged all of the input. Yeah, that's the idea. Yeah, that's one way of organizing that. Yeah? So basically, if you go back to this example, so again, pass 0 ends here. We have all of those runs. So the heap would have 4 entries, organized by size. So 2 pages, they all have the same priority. It doesn't matter. It will pick randomly 2 of those, could pick any 2. In the visualization, it's the first 2. They are merged into this one. Yeah. So on the next iteration of the loop, the heap will pick the 2 smallest runs. Oh, these 2. Yeah, they will be merged into that one. Next iteration, the 2 smallest are those will be merged into that one. Now that creates a level-wise merge tree. You don't have to do it like that, but that's one way of doing that. Yeah, that is external merge sort. Okay, and important here in this algorithm, of course, you use the main memory algorithm to sort the stuff for this pass 0. Yeah? And in the following, we will look at an interesting alternative for main memory sorting. That should show up here. That's called replacement selection. So basically what you saw in this example I just showed, well, if you have 2 input pages, what is the size of the output run? It's 2. Surprise, surprise, surprise. Yeah? And what I'm showing you with replacement selection is there exists a main memory sorting algorithm that will create, on average, runs that are bigger than the available main memory. Why would that be interesting even? So assuming this wonderful algorithm exists, so there's a main memory algorithm that, given a couple of pages, is not restricted to a number of pages I feed in, is a number of pages I output, but there's an algorithm that may create more pages than available in the input. So without, you don't know the algorithm yet, we will go to that in a minute, but just thinking about that, what would be the impact of an algorithm like that in this algorithm, in external merge sort, I mean. Why could that make a change? Well, if I have an algorithm, assume that creates double the amount of output, even though I have only 2 pages available, that could reduce the number of merge levels in the algorithm. If my algorithm magically can output in a single pass 0 operation, sort all of those 4 pages, even though I have only 2 pages of memory available, I have bigger runs and I will have fewer runs. If I have fewer runs, the likelihood increases that the merge tree is flatter, that is not as deep as before, which means what? In terms of cost for the algorithm. Less read and write operations. Here in the example, which is completely made up, of course, I save 1 read and 1 write operation. So if you compare that with the stuff before, there was this extra merge phase where I would merge the 2-page runs into 4-page runs. Now I can skip over that directly. So I save an entire write of the input data and an entire read of the input data. That's a huge difference, or maybe a huge difference again on the slowness of your storage devices. So how would an algorithm look like that can create those bigger passes? It's called replacement selection, was first mentioned by Donald Knuth in his books. And in this example, we process data from the right to the left. So the input sequence I'm looking at is this. This is my input sequence. And I will start processing that sequence here with a 30, 20, 10, and so forth and so forth. And that is the output run I'm creating. And the assumption here is I have capital M equals 4. That is only 4 entries available in, also 4 integers I can put in main memory at all times. So similar to the previous example, where I had those 2 pages having 2 integers each, I have 4 integers I can keep in main memory. And what I'm showing here is basically a heap in main memory and a list. So it may appear that, okay, it's 4 in the heap, but 4 in the list. That's not true. The only condition I need to preserve is that the number of elements must be smaller, equal that m, so that 4, that looks as if it were 8, and you would argue, oh, there's an empty entry that still consumes some memory. No, in a real implementation, you merge those into one structure, and part of the structure is organized as a heap, and the other is just the list. Just for explaining it conceptually what I'm doing, I split it up here. Makes it easier to explain. So we start by filling up the heap with the first 4 elements. So here are my first 4 elements. Let's put them in the heap. Okay, the heap will create that half order, hard to show here. So I fully sorted, basically create an order on the elements, something like that. So the heaps are sorted, the elements in the heap are sorted, 10, 20, 30, and 40. Now the actual replacement selection algorithm starts as follows. I take the first element and I set it to be the last element on the output. That's always denoted here on the left. Last element on the output had the value of 10, this one. And what I do is I compare this value with that value. That is the case. 25 is bigger than 10, so I can simply insert the 25 in the heap. The heap now has room for 1 more element. I just removed 1 element, so I can insert another element. That's what I'm doing in the next step. Now the 25 gets inserted, and you see already, if you just now simply wrote out those 4 elements, like appended to that output run, it would already be 5 elements rather than 4. Even though standard quicksort could only produce a run of size 4 elements here in this case. Now I continue. So again, I remove the smallest element from the heap, 20, send it to the output. Here we go. Record it in that variable. And again, do this comparison. Well, is 20 smaller 73? Cool. Then we can insert 73 in the heap again. There's room for 1 more element. That's what I do in the next slide. Now our heap still has a size of 4 elements. And so on and so on. Eventually, I come in a situation like that. So here, from here, if you're here, we would remove the smallest element, 25. Okay, we send it to the output stream. Here we go. And now again I do the comparison whether this element is bigger than that one. This is smaller, that is depicted here. So I don't put it in the heap. That is the trick in the algorithm being played. Now I'm saying, now the 16 goes to the list, to this extra list, and my heap is decreased in size. So the heap only has a size of 3 elements, and the list has a size of 1 element. 1 plus 3 is equals 4. So why on earth is it that this 16 is not inserted in the heap? Does anyone see it? Yeah?
Because on the next iteration, 16 would go into the output and then
Yes.
we update it.
Perfect. Perfect answer. Yeah. In the next iteration, if I had put 16 here, yeah, then it would be set. It's the smallest element will be removed, will be appended to that output, and then that wouldn't be a sorted output run anymore. It would have be 10, 20, 25, 16. That doesn't make any sense. It's not sorted. Yeah. Therefore, you always make those comparisons. Yeah? So if you continue with the algorithm, 16 goes to the list. Again, you remove the smallest element, 30. 30 goes here. Yeah, again you do the comparison. 30, oh, that's bigger than 26, so 26 will go to the list. 26 will go to the list here. The heap size is decreased. Now it's only 2 elements. Here's 2 elements in the list. Yeah? Again, you remove the smallest element from that heap. That is 40. Send it to the output stream. Again, do the comparison. Again, you're unlucky. So 33 will go to the list on the next page. It's the next slide. Now there's only 73 left. You send 73 to the output. Here we go. Make the comparison. 50 is smaller than the algorithm. Yeah, then you load 50 into the list, of course, still, yeah. That's where you are, but you don't have a heap anymore at that point in time. So here, in this situation, the algorithm terminates for this particular run, which means the heap is empty, the list is full, and you can't produce any element that's bigger than 73 anymore. So that marks the end of that run. Yeah, you created one run, and now you would have to continue by starting a new run. Yeah, but you can't continue with this existing run. So what you do is you copy all the elements that lived on the list here before. Yeah, those are the 16, 26, 33, and 50 are now moved to the heap. Yeah, again, as it's in a real implementation, it's the same array anyway. You don't move anything. You just say now my heap contains 4 elements. You create the heap property, the half order here shown as a sorted order. You start from scratch with a new run. Am I showing that? Yeah, here you create a new run, output 16, but you have to be careful if you write it here to the same output stream. Of course, there's a boundary here. Yeah? So you could also send that to a separate file if you wanted, as shown in the previous variants of external merge sort. Yeah? That basically here is a new run starting. There's a hard boundary. Yeah? And then you continue, 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 continue. Isn't that cool? Pretty cool, right? Yeah, so you get larger output runs. On average, it's about double the size. Depends a bit on the whether there's pre-sortedness on the data. This for sorting in main memory, replacement selection is typically somewhat smaller because it's relying on a heap. And even though the heap is optimal, yeah, heap sort, for instance, is optimal, it's not very cache efficient. Therefore, you lose a little bit. But if you save on I/O, that amortizes. You save these, depending on how much you save. It's hard to say, but it can save quite a lot And that's the interesting thing about the algorithm. So in practice, basically, you have to do experiments to find out whether that works well or not. Yeah, here's the pseudocode for that. Do you want to go through that? I mean, the trick is this one. Yeah, we're doing the comparison. What I output, what is the last element being output? If I compare that to the first element in the input to be processed, yeah, is it smaller or bigger? And then you just always make to have a decision. Okay, routed to the heap or routed to the list. That's the entire trick. Yeah, and if it's bigger than what you just output, well, no problem. Just insert it into the heap. It's fine, right? You can produce it eventually. So basically, every time you can insert something into the heap, again, yeah, you increase the length of the output run to be produced eventually by one element. Yeah, and that's a pretty cool algorithm, actually. Yeah, let's look at some variations. So one of those I already showed you in the first half of today's lecture. So how would you do something like, sorry. How would we do a query like this? Select A, count star from table group by A. Yeah, so for all tuples that have a value of A, make a count star. And let's assume that I only have one attribute here because it's just stupid integers in the example. Basically, that means I want to count the occurrences of each and every integer in the input. Yeah, let's read it like that. What could I do to improve external merge sort to support the query? Yeah? So what I'm saying is the database system could initialize external merge sort as is, yeah, like a library call, but there are many implementations that allow you to inject code and play with the algorithm and modify it slightly to play tricks. And if you have a query like that, which trick could you play? And we have seen it before. Old tricks. You remember run length encoding? If we did want to switch over to that one. What was run length encoding? So if my schemas really, I only have attribute A, okay? And I want to group on A count star. So for each distinct value of A, I want to count the number of occurrences. That's what this query is saying. So basically, if that is the data, so I would count the number of ones. Yeah, 1 appears twice, okay? 2 appears once. 3 appears twice, right? 4 appears 3 times. 5 appears once. 6 appears, and so forth. Get the pattern? So if you have a sorted stream of those integers and represent it like this, I would call that run length encoding, right? You recall the compression algorithm, yeah? Sort symbols and then only keep the symbol once and counts the number of repetitions. This happens to be exactly the same thing. Yeah? So what could you do in such an algorithm? If you know that is the only purpose of sorting the stuff in the first place is that you made a decision somehow to do a sort-based grouping rather than hash-based. So that's why you sort. You're not interested in the sorted data. Who cares? You're just interested in answering this query. So if you know that, how could you change this algorithm? Or stand up and do some sports to me. Christmas is coming up. Huh? Come on, make wild guesses. Or should I re-explain something? I don't know. Yeah.
Are we allowed to output one
You mean here? Yeah, why not? I don't care.
Okay. Then instead of sorting them, we could have, for example, there we have 2, 3, 4, 4, 6, 7, 8, 9. Then we would have 2, 3, 4, 6, 8, 7, 9. And then the second integer would always be the amount of times we saw that element.
Yeah. So what we're trying to say is, rather than first writing the sorted data out to disk, reading it, and then doing the actually sort-based grouping, you want to marry it somehow into the merge operation. Exactly right. That's what you could do. Why not? It's the same as with a sort merge join again. You have a sorted stream of data. No one forces you to write out the entire sorted stream. You can directly operate on the sorted stream. Again, you identify a group, as explained in sort merge join. Once you close the group, you have this count, yeah. And then rather than writing this, writing 2 ones to the output stream, you just write this run length encoded tuple, 1, comma appearing twice, and then 2 appearing once. That's true. You could do that in this merge operation. Good. More proposals. I mean, here it's a bit yeah. If you go back to I recall the algorithm here we did with quicksort. Well, there were a couple of more merge operations, right? You could do it here, you could do it here. We just did it here. You could do it with any merge operation. You're not restricted to that. The first merge you do, you don't output the sorted data. You just already, you find 2 ones. Hey, I converted into a run length encoded tuple, for instance. They could do that. So that's one message here. You do it with each and every merge operation. But there's another opportunity. Where are we? I'm lost. Here. Where else could you do something? I mean, what does this first phase do? It produces a sorted output stream. Yeah? So what is a precondition for being able to using sort-based grouping? It's a sorted output stream. It can be partial. It doesn't have to represent all of the data. But that means whenever your algorithm produces some sort of sorted output stream, hey, you can do the run length encoded trick. Yeah, so even in the pass zero, in external merge sort, you could already start, rather than producing the data, you try to produce those tuples. For instance, here, the 4 could be represented as 4.2. I mean, in this textbook example, and that's maybe what you said, or can I produce output runs that are bigger? You have to be careful. Yeah? If you don't find enough duplicates to compress them into a run length encoded format, it's the same problem as in the standard run length encoding. Yeah, if you have no duplicates whatsoever, you will considerably blow up your data by always adding a 1. Yeah? Whatever symbol 1. Yeah? So there's a trade-off. Yeah? So it might be that depending on the statistics of the data, you say, okay, the first merges then, or the first phases, you don't do anything special, but the later merges, you realize, oh, I could do something. I could already start aggregating while merging. So this is called early aggregation, and another very interesting technique. Yeah? It's again visualized here. So the standard grouping would only happen after producing the sort, but you could, that's visualized what I just said. You could also marry that into this merge operation. That's what the slide show. I do it at any other point in time. In particular, my count star is super easy. Yeah, here's another extreme example. If you don't group, what happens? If you just do a count star without the grouping, basically just counting the tuples, it doesn't make any sense anymore if you want, because you don't have to You only have to load one page in main memory. You don't have to partition it. But if you want to do it with something like external merge sort, it basically means that the first instantiation in the path 0 produces just the count of tuples. The second as well, you merge two integers into such a tuple and you create 16. Yeah? But it's kind of ridiculous, of course. For just counting, you would simply scan the input set. If you don't have metadata or statistics, that would do the same thing. Okay, so summary for query processing. There are 4 principal paradigms of join algorithms: nested loop, index nested loop with this important special case simple hash join, sort merge join, and partition-based, not covered today, well, kind of. The co-grouped is a partition-based join algorithms. Important for you to understand is similar algorithmic patterns can be used for other relational algebra operators like grouping, aggregation, intersection, difference, co-grouping. Yeah, all these set-based operations you find in relational algebra can all be mapped to those algorithmic patterns. External sorting and external partitioning are key algorithmic patterns to master data bigger than main memory. Yeah? Whenever you are in this situation that you shuffle data around on a big cluster or into memory back and forth, it's always one of those algorithms, and the patterns appear over and over again. And in particular, this duality between partitioning and merging, yeah? Like in sorting. You can sort by partitioning, you can sort by merging. Yeah? You can group by partitioning, you can group by merging. You can do it recursively, as in merging recursive merges. You can partition recursively. You have one partitioning round, and then on each of the partitions, another partitioning round. Yeah, it's the same patterns that appear all over again. So, which is good news. That's not that you have to learn about 10 complex algorithms. It's more like algorithmic patterns you see reappearing all over again. Once you master those, it's super easy. Yeah, so and that's more the advanced part we looked into. Yeah, it's not the first thing you do, but you could do that in many situations, fusing algorithms into one another. Yeah? So, throwing away the strict boundary of, for instance, sorting and joining, merge joining, sorting and merge joining, or aggregating. First creating this sorted output stream and then running the sort-based aggregation versus injecting logic from the sort-based grouping and aggregation into the merge tree and into the external merge sorter. Can be done, not the first thing you want to do, but could be helpful. Okay, with that, we start with slide set 6, query optimization. Yeah, we're still here, and I underlined where we are going. So we looked at this one now. Now we will look a little bit more into how the pipeline can be organized. So how data is pushed around or pulled around in such a processing pipeline. We will look at cost-based optimization. So the rule-based part we don't do in this lecture anymore. I had that in the repetition part early on. And we did it already in the undergrad lecture anyway, because it doesn't really play a role. It's cost-based optimization these days, the state of the art. Yeah, so let's start with that. And let's first focus on some challenges in cost-based optimization. So one is join order. We already touched that briefly in the undergrad lecture. Some of you might not have seen it, so that's one reason for repeating it here. So assume you have a join on 2 relations, A, C, and B, and as those joins in relational algebra are considered binary, so typically you end up in situations like that. You have to make a decision on which join to execute first. And that may make a difference, or not may, it makes a difference in reality in which order you execute those joins. So in that example, all input relations have the same size. They all contain 1,000 tuples. That is what this cardinality relation, that always gives you the number of tuples in the database world. So here we have 1,000 tuples that go into the left side of this join, and that holds for all the other relations as well. So this gets 1,000 from the left, 1,000 from the right. But what may happen is that this join operation produces a large intermediate result, like in this case 100,000 tuples. Yeah? And that will then be used as the right input to this operation. And what we will be using in the following is a rationale where we say, okay, can't we minimize the intermediate result sizes? Yeah? So if I have a situation where I first join A with C, and the intermediate result only contains 100 tuples, that makes this join so much cheaper, yeah? Because it's not like here 1,000 plus 100,000, but just on the right side here we have 100 plus 1,000 tuples from the right. Yeah? So depending on how these input sizes determine the cost of such an operation, it's very likely that that join will run cheaper. And of course, I want to create a plan that is fast. Yeah? So the question will be, what is the fastest plan? So the discussions we will be having is, okay, given a SQL, how do you come up with a plan, or how do you come up with a specific order of the joins? In which order do you execute those joins? And there's a lot of thought that you can, many thoughts you can spend on that. Yeah, other problems you have in query optimization is, yeah, if you have a query like this on the left, yeah, you filter on some condition, then you project to title and ID, then you have a join, equi join on B, and then you project again. Yeah, here you have your input relation A, and typically you don't want to do something like that. Yeah, that comes directly from a where clause typically, yeah, where you in the where clause you write a.name equals Hugo. But you don't want to read all of A. Yeah, that's typically way too expensive. Scanning the input relation is something you want to avoid. So we use one of those indexes we learned about. And I don't know, it's about data layout, sorry. So you could think about, okay, if I'm only accessing one of the attributes, yeah, a data layout that's column-oriented is much better, yeah, because I would have a column just for the name attribute here. If my attribute, if my relation A is 100 or whatever, even just 10 attributes, yeah, but I'm only doing this operation on one of the attributes, it might already be beneficial to have a column layout underneath. So that's what I'm trying to depict here. Yeah? So the layout may have an effect on the performance of a scan, even though I don't use an index. Yeah? That's one thing. And the other is indexes. So basically what you do in indexes is you try to get rid of those expressions and replace them by an index access. Here depicted as an upside down tree. Yeah, so this confusion with tree, yeah, we always, the tree grows on the ground, yeah, and then gets broader, wider and wider, which is trees are doing it wrong, right? They're completely doing it wrong. It must be upside down, right? Like, why is nature doing it like that? Because the trunk must be on top. The root is on top, right? And then they grow downwards. They don't do that outside. I don't know why. I mean, very weird how trees are doing. Okay, yeah. So that's why I'm depicting it like this. Okay. Yeah, and then the difficult part is we had this clustered versus unclustered index. And that's one of the bigger challenges. You also see these things go wrong in practice, real systems, real database systems. So making a decision on, okay, you have an index that is clustered. And as you remember, okay, clustered means on the leaf level, the order of the keys is the same as on the data store. That's cool because you can do a sequential access and then first a random access, the entry point, and then you scan. Not much random I/O. But if it's an unclustered index, then these arrows here go crisscross. So potentially for each and every lookup, you may have a random access. And that may be really, really expensive. And that, if you don't take the right decision, if you take the decision in query planning to use an index like that, you may end up with plans that are slower than scanning. Yeah? So accessing the index may be slower than blindly scanning your data in the first place. Not only by 10 or 20%, but by a factor. Why? why can something like that completely ruin query performance? And that happens in practice. Query optimizers getting it wrong, taking the wrong turn, going for a plan like that. Customer is surprised, hey, it's 5 times slower than before. How did that happen? I just created the index. Index makes it faster, better complexity, blah, 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 blah. 5 times slower. Yeah?
Maybe when the condition is too broad, we have a lot of like random accesses.
Yeah, random accesses, right. Yeah, if the condition is broad, meaning the index is not very selective, many tuples qualify, meaning, yeah, in the worst case, 1 random access for each and every lookup in the store. Yeah, and you remember random access on a good old hard disk, 5 milliseconds. Okay, SSD much faster, but it's just a constant. If you have 100 times or 500 times more qualifying tuples, that won't make the difference. Yeah, that will slow down matters. Okay. Yeah, here, okay, yeah, that's just to illustrate that we will run into the problem that in order to make decisions, yeah, so what I'm showing you are basically plan alternatives on how I could execute such a query. But then eventually I have the problem, okay, which plan am I going to take? Yeah? So I just told you, taking the index, no, you can't just take the index like that, because there may be cases where you ruin performance. So basically the problem we will be having is, given such a plan, without executing it, I want to have an estimate for the costs, the runtime, if you wish. Yeah? I want to have a wild estimate that tells me, okay, so this may cost, I don't know, just making up numbers, 42 seconds. This will cost 70 seconds. And that will be whatever, 10 seconds. They're just making up numbers. And then you have those estimates, and then that's the smallest value. I will execute this plan. Yeah, that happens at large scale in a query optimizer. Whenever you submit SQL to a decent database system, it will enumerate tons of those alternatives, will then predict the costs for each of those alternatives and simply execute the alternative with the smallest cost. So. Well, that's a fundamental problem in query optimization. Yeah, and here again, that's basically this index access problem, again, visualized what that means. So selectivity is a term we use to describe how many tuples qualify under a certain operation, in particular on a selection. Yeah? So if you have a selection like that, and if you select something on a key, for instance, yeah, there can only be 1 tuple being result. Yeah? That's the definition of a key. Yeah, but if it's a non-key attribute and you run a filter, anything may happen. Yeah? If you have a student table on whatever the university's lecture system, yeah, and you filter all students that live in Saarbrücken. Maybe that's 1/3 of the students. That's many tuples. Yeah, or everyone studying computer science. I don't know how many that is. There's many more tuples than just 1. If you a student with immatriculation ID, whatever, that's 1 tuple. Yeah? So that's described by a term we coin selectivity. There are various definitions for that. I think later on we will show that. But basically, it leads to curves like that. So if you vary the number of qualifying tuples from few results qualify versus many results qualify for the selection, just looking at this selection, you can compute the costs depending on this selectivity. Yeah, if you only have few results, yeah, then basically in this space, the unclustered index seems to be a good idea. Cool, yeah? Much better than scanning it in the first place. Whereas when you scan, it's basically a constant. Yeah? You scan the input, it's linear costs in the number of tuples. There's no variation. It doesn't depend on whether tuples qualify or not, because the actual cost is reading the data in the first place. Yeah? And then you get curves like that. And what you want, and the problem we're trying to solve, and what a database system needs to do, is model those curves such that they correspond with reality. And whenever I am in a situation that I have plan alternatives, I always want to hit this space. Yeah, basically the curve that dominates. Maybe I wait till this is removed. It's easier if I go away, wait 3 seconds. So basically he hit this curve here. Yeah, so there's a point here. Up to that point, the database system should use the unclustered index. Beyond that point, it should use a scan. Yeah, then it's optimal because I always use the best plan that's possible in that space. Yeah, that's the task of the query optimizer. And again, as alluded to before, there have been prominent cases where database systems got this wrong. Yeah, so the previous performance was this. Then the user created an index. Now the index was available, unclustered index, available to the optimizer. Cost estimates were wrong, and the optimizer moved this point here, which would say, okay, up to this point, I would use the unclustered index. So if you had a query in this space, all of a sudden, the query would run slower than before. Yeah?
I have a question. After we get the index from the unclustered index, after we got the result, can we, before we send it to get the tuples, can we first to sort the result based on the offset?
Yeah, you could do that. As you mean you just access a leaf. No, you don't, when accessing a leaf, you don't go directly to the store, but you just collect all the entries from the leaves, then you sort them, and then you go to, yeah, very good idea. Yeah, you could do that. Yeah. Some systems actually do it like that. That's basically, in particular, this will pay off the more results you have. Also, assume the case that, so if you do it naively, yeah, if you, for instance, is an example here. I think here's a good example. Assume you end up with the same page from 2 different leaf pages here. Yeah. Okay, let's hope the database buffer will do the trick, will do the magic. But in theory, it could happen that you load the page from the store here once, and once you're here, the page was evicted from the database buffer, and you have to load it again. Yeah, so in your example, if you sort it by the page IDs, yeah, and then do it in ascending order, in particular sort it using the same order as used in the store, whatever that order is, yeah, then you would save something. That's a very good remark. So in particular, the more tuples you have, that technique will pay off. The same also applies for B trees, by the way. So, yeah, we have this example that's kind of related, where I showed to you where motivated bulk loading. I said, okay, rather than, so if you have the random order of inserts, you could insert it, would create the splits. Now, if you sort it first, yeah, then basically it has a similar effect on I/O. It has some benefit, just that leaves are half full. Yeah. These kind of things, yeah. Very good. Okay. Where was I? Good. So let's look to this again. So basically here, shall we start with that? That's basically what I explained before. Yeah? So given certain selectivities of these operations, the intermediate results can be big. Yeah? That's what we had before. And you try to estimate those costs. Again, here's a high level, the overall idea of cost-based optimization. You enumerate plan alternatives. For each plan alternative, you estimate the costs. You pick the plan with the lowest estimated cost, and then you go for that. You actually execute that. Yeah? You don't execute all of those plans, just the cheapest. And the problem here is that the search space can be relatively big, yeah? Depending also on something else I will show in a moment. Yeah? But if you just think about that combinatorially, then you will see that can be rather big. Yeah? Just for left deep trees, so left deep tree meaning you always start with two relations, and you add another join, zack, to the next relation, add another join, zack, to the next relation, another join to the next relation. That's a left deep tree. adding one relation after another, here from A to A, B, E. This is not a left-D plan, that's called a bushy tree. So here you see first A and B joined, then D and E, then A and B with C, this part, and then the result goes into this one. That's a bushy plan. So there are different binary structures. So you can just reason about, okay, which binary trees are possible. So given a certain number of input relations, how many binary trees are possible? And that's what I'm trying to visualize here with all these colors. So this shows all the binary trees that are possible with 3 input relations. So just the possibility to join the first 2 relations, and whatever the result is with the remaining relation, or first join relation 2 and 3 and the result with the left input. That's for 3 inputs, 2 possibilities. For 4 inputs, we have this. We have again this pattern, first 2, second 2, join everything. Or we have a 3 pattern, one of those. Yeah, those are 3 relations. That's kind of dynamic programming argument I'm making here. Yeah, and whatever is returned from that, join it with another relation. Yeah, and the same here, just mirrored, and so forth and so forth. So if you have 5 inputs, you could do it by joining a 4 pattern with a 1 pattern, a 3 with a 2, a 2 with a 3, and so forth and so forth. So you see this search space is exploding, and mathematically, okay, for bushy trees, it's commutative. They have to be careful. But mathematically, how you can compute this is by the Catalan numbers. Yeah. So do you have another slide on that? Oh no, that's already the extension. Yeah. So that's the number of structural binary trees that you can compute. Yeah. So basically, you always have to use the Catalan number decreased by 1. So if it's 2 input relations, you compute C1. What can you do with C? I mean, it's 2 inputs, right? It's join, right? There's no structural difference. So if it's 3 relations, there are 2 possible trees. For 3, it's plus 1 always. For 4, it's C3. For 5, it's C5, and so on, of course. Right? Yeah. With that, you can compute the number of binary trees. But then, even though you did that, yeah, we still didn't look at, okay, in which order do you write the relations on the leaf level of that merged tree? Yeah, I'm using it from A to E in ascending order, but you could do that in any order. So basically, only if you look at 3 input relations and have such a 3 pattern, we have 2 of those patterns, I can label that in the order ABC, ACB, BAC, and so forth. Yeah. So number of relations, what's in English? Faculty? No, not faculty. What is Fakultät in English? Factorial, right, yeah, thanks. Factorial, yeah, of the number of relations. So this is 3 factorial. Yeah, 3 times 2 times 1, 6, yeah, 6 different possibilities. Right, yeah, so basically the number of possible plans for 3 relations is the number of structural binary trees times number of relations factorial. That's the number of possible plans, yeah, and that goes through the roof pretty quickly. I mean, one thing to worry about could be this one. In the enumeration I showed before, those 2 plans would be counted independently. Yeah? So in these 3 patterns, this is a completely different tree pattern on the left than on the right, of course. Yeah? But as I enumerate all possible labelings for those relations, yeah, I will once have this on the left, this on the right, but both are semantically saying, whatever you do, I first join C and B, and then I use those as an input for the next join with A. So that's the same plan. I counted them twice. Yeah, do you see that? If you, yeah, again, this thing, yeah, I did this and this. I have ACB and CBA, okay. CBA here and ACB. So this is counted twice in this mathematical argument on the number of different plan alternatives. So does that make sense? Yes or no? And why am I sure that the answer has something to starts with it depends? When would that make a difference and when not? So the plan alternatives exist in that space. I just sketched that space. They are there. But now if you are in a real query optimizer and want to think about, okay, should I consider those plan alternatives that will blow up your search space? Should I do it? Is it worth doing it? On what could that depend? Yeah, didn't see you.
It depends on the join algorithm. So in case we have a hash join, then we would each materialize the left side, which in case of the of plan 1 is just 1,000 keepers, and
Yeah.
of plan 3 it's 100,000 keepers, so there it matters. If we have a different join algorithm, it might not matter.
Yeah, excellent. Excellent answer. So it depends on the algorithm. It depends on the symmetry of the algorithm. Hash join is not symmetric in the sense that on the left input we do something different. We build a hash table. So if the left input is rather big, like in this one, yeah, I will build a hash table on 100,000 tuples, whereas here I will only build a hash table on 1,000 tuples. Yeah, and this is definitely much more costly in my memory than this one. Runtime maybe with a hash join is not such a big deal here, yeah, but this is 100,000 tuples in my memory, whereas 1,000. The others are just streamed against that. That's the difference. Yeah? So that's an asymmetric algorithm, whereas, for instance, so what would be a symmetric join algorithm? It does the same processing on the left as it does on the right. And it really doesn't matter. There's no left and right. There are two inputs. Both are treated equally, which is not true for simple hash join, but there's one algorithm at least that's treated equally, where the inputs are treated. Is that a, no. Kind of? Huh? Depends on the I/O pattern you use underneath. Let's say it's difficult. Relationship status, it's difficult. Because it depends on, let's say no, okay? Can be, doesn't have to be. Okay. You?
I don't remember the name, but the one with the partitioning you showed.
The co-grouping? Yes, that's one example. Co-grouping is a very good example. Co-group join you can be symmetric. That's true. Yeah. I want to say, okay, good. I didn't look at co-grouping. Why not co-grouping? I had a different algorithm in mind. But co-grouping, nothing against co-grouping because you partition on one of the inputs. Doesn't matter which one first. Of course, we had this exercise where you had to play this trick and keeping stuff in the memory, blah blah blah. Yeah. But in the general case, it doesn't matter which you partition first. Eventually you have the co-groups. Yeah, sure, that's true. The other is sort merge join. Yeah, doesn't matter. Same thing. Cool. Yeah. I think in 1 minute I don't explain cost-based optimization. Yeah, so let's call it a day. See you on Friday. Yeah?